When a massive star dies, it doesn't disappear, it transforms. In the silent aftermath of a supernova, something even stranger is born: a neutron star. Tonight we'll explore how death in the cosmos gives rise to new extremes of matter. If you enjoy these journeys through space, please like, subscribe, and share, and tell us in the comments which cosmic event fascinates you the most. Thank you for watching. Now let's begin. In the depths of space, a massive star approaches the final moments of its long equilibrium. For millions of years, it has maintained balance between the inward pull of gravity and the outward pressure from nuclear fusion in its core. The cycle of fusion has passed through every available stage: hydrogen to helium, helium to carbon, carbon to oxygen and beyond. Now only the innermost region continues to change. Deep within, where temperatures reach billions of degrees Celsius, the fusion of silicon atoms forms iron. Each reaction occurs in the last stable layer of a complex onion-like structure, with the lighter elements outside and heavier ones within. But iron is different. It cannot produce energy through fusion, and so the reactions that once supported the star begin to fade. The balance between heat and gravity weakens, and with it the long-lived equilibrium that has defined the star's existence begins to dissolve. As silicon burning proceeds, the pace accelerates beyond comprehension. What took millions of years in earlier stages now unfolds in a matter of days. The iron core grows heavier as more matter sinks inward from surrounding shells. Each atom that fuses adds mass without adding pressure support. The core becomes increasingly unstable, dense beyond the capacity of normal atomic structure. The inner pressure no longer comes from heat, but from the quantum forces that resist the compression of electrons. This pressure, called electron degeneracy pressure, is powerful but finite. As the iron core grows beyond a critical mass, even this resistance begins to fail. The star is now in a delicate and temporary balance, holding its form for only a few more heartbeats of cosmic time. Outside the core, the outer shells of the star continue to burn in concentric layers. The surrounding material, carbon, oxygen, and neon, still glows from the last fusion reactions. The entire structure resembles a living organism, sustained by processes that no longer communicate properly. The energy from the core no longer replenishes the layers above it. The star's outer envelope remains vast, spanning millions of kilometers, but inside the chain of stability has already broken. It is as if the star's heart has grown silent while the body still moves. Within the iron core, conditions tighten to extraordinary extremes. The density rises until a single cubic centimeter of matter weighs hundreds of millions of tons. Electrons are forced into atomic nuclei, merging with protons to form neutrons, and releasing neutrinos in immense quantities. This transformation marks the end of the atomic structure itself. The process removes the last source of pressure that could resist collapse. Gravity gains complete control. The speed of inward motion increases rapidly from thousands of kilometers per second to a near relativistic plunge. The material of the core falls freely toward its center, accelerating as if nothing remains to stop it. The final seconds of this collapse occur with astonishing violence. The inner core, unable to compress any further, reaches densities comparable to an atomic nucleus. At this point, the neutrons themselves resist further compression through their own degeneracy pressure, the final quantum force available. When the infalling matter strikes this incompressible core, it rebounds outward, sending a shock wave through the surrounding layers. This brief reversal, lasting only a fraction of a second, marks the instant where the dying star begins to transform into something new. Yet for now, the shock front still faces overwhelming resistance from the mass falling behind it. The structure that once held millions of years of fusion energy now folds inward upon itself, releasing more energy in a single second than the sun will radiate over its entire life. During these last moments before full collapse, the interior glows not with visible light, but with neutrinos, nearly massless particles capable of escaping through dense matter. In the space of a few seconds, a burst of neutrinos carries away a significant portion of the star's gravitational energy. Though invisible, this flood of particles signals the imminent death of the star and the birth of a new object beyond ordinary comprehension. To an observer outside, there is no clear warning. The surface of the star, still many layers removed from the core, has not yet reacted. It shines as before, calm and steady, unaware that its foundation has already vanished. Inside, the transformation continues at speeds that defy ordinary sense. The density climbs, temperature spikes, and the core contracts until it reaches only a few tens of kilometers across. The collapse is total and unstoppable chain of physical responses to the breakdown of thermal equilibrium. At these pressures, matter behaves collectively rather than individually. Nuclei dissolve and particles exist in a dense sea of neutrons and exotic forms of matter. The core becomes a proto-neutron structure before the outside universe can even respond. The gravitational potential energy released in this process is vast enough to unbind the entire star if it can somehow be transferred outward. For the outer layers still untouched by collapse, the process is invisible but approaching. The surrounding shells begin to follow the core inward as gravitational pressure propagates outward. Layers that once burned quietly in fusion now descend toward the center. Hydrogen and helium from the outer envelope fall through the deeper zones, compressing and heating as they move. In this final hour, the whole star becomes a cascade of infalling matter. The forces binding it together are stronger than ever, but now they work against the survival of the star itself. Even in these catastrophic moments, there is a strange order. The physics that governs this collapse is absolute. Each stage follows naturally from the previous one, an inevitable progression, dictated by the laws of energy and gravity. There is no chaos in this destruction, only inevitability. The star's internal layers, formed over millions of years of fusion, are now collapsing inwards over the span of a single second. The energy once locked in nuclei in radiation, in pressure gradients, now converges toward a single dense point, where a new kind of stability may soon arise. Far above the collapsing core, the outermost layers still radiate peacefully. They have not yet felt the change. Light continues to travel outward as if nothing below has shifted. To a distant observer, the star appears unchanged. Only deep inside does the transformation race toward completion. In less than a moment, the star's structure will reverse itself. The implosion will meet the hard resistance of nuclear density and generate an outward shock, a sudden release of pressure that may tear the star apart. What follows will define the rest of its existence and give birth to one of the universe's strangest remnants. The final hour ends not with an explosion, but with silence. Every element of the star's core now moves inward, every particle obeying gravity's command. In that silence, a singular change is about to begin, the transition from living fusion to the cold compression of degenerate matter. The birth of a neutron star starts here, hidden beneath layers of gas within a moment of perfect collapse. The outward light remains calm, but the interior has already crossed the threshold. Within seconds, this collapsing core will meet the density of nuclear matter and create the first shockwave, beginning the sequence that will end one life and begin another. In the interior of the dying star, the final resistance ends abruptly. The iron core, now surpassing its critical mass, yields to gravity in a sudden implosion. Within a fraction of a second, matter that once formed a stable lattice collapses inward, falling freely through a collapsing sphere that shrinks faster than light can escape the surrounding layers. No outer sign betrays the event. The luminous surface remains tranquil, but deep within density rises to levels approaching that of atomic nuclei. Electrons are crushed into protons, forming neutrons and neutrinos in a cascade of weak nuclear reactions. The star's inner structure changes from atomic to subatomic order, its particles reassembled under intolerable pressure. The collapse accelerates without pause. The inward motion of the core becomes a runaway process. As each layer compresses, gravity strengthens, drawing more mass inward and hastening its own momentum. The material freefalls toward the center, and in less than 1 second the core shrinks from thousands of kilometers across to only a few tens. In that instant, the energy balance that once held the star together ceases to exist. The loss of electron degeneracy pressure leaves gravity unmatched. Matter accelerates until it meets the central region, where compression can proceed no further. At that density comparable to that of an atomic nucleus, the strong nuclear force halts the collapse. The innermost core rebounds outward. The shock that forms at this boundary is the first sign of a reversal within the implosion. The new shock wave races outward, meeting in falling material still plunging toward the center. For a moment, the motion of collapse and the force of rebound coexist, creating an unstable frontier within the star. The pressure and density are enormous, with temperatures exceeding several billion degrees Celsius. Photons cannot travel freely in such density. The region becomes opaque even to neutrinos. The matter here behaves as a hot, degenerate fluid composed of neutrons, protons, and nuclear fragments. As the shock advances, it compresses and heats the overlying layers, but each encounter with fresh infalling matter drains its momentum. The collapse of the outer core continues to feed mass into the shock, increasing its burden. Behind the shock conditions are chaotic yet precisely ordered by physics. The newborn proto-neutron core continues to radiate neutrinos as weak interactions convert protons into neutrons. These neutrinos carry away vast amounts of energy, but the energy escapes unevenly. Some are absorbed by the surrounding material, altering the energy balance of the region. The pressure they exert becomes a crucial factor in what follows. For now, however, the energy lost through neutrino emission dominates. The shock begins to stall. It loses power and drifts outward without reaching the outer layers. The supernova explosion has not yet succeeded. At the same time, within the deepest zone, the proto-neutron star begins to form. It consists of matter compressed to nuclear density so dense that atomic nuclei cannot exist as separate entities. Neutrons dominate, packed together by gravity and balanced by quantum pressure. The inner region is less than 30 kilometers across, yet contains more mass than the Sun. Its temperature remains above 10 billion degrees Celsius. The surrounding region, the hot mantle, extends outward to 100 kilometers, filled with trapped neutrinos and heated plasma. The boundary between these regions becomes the site of intense energy exchange, where neutrino diffusion and hydrodynamic motion interact to shape the young remnant. Above the shock, the rest of the star continues to collapse. The infalling material, once part of the envelope and burning shells, moves inward at enormous speed. Each layer compresses the ones beneath it, creating concentric waves of heating and compression. When this material reaches the shock front, it suddenly decelerates, heating further and adding to the density of the region. The pressure gradient grows steep, yet the shock lacks enough power to break free. For now, the outer layers remain bound, waiting for an additional energy source to restore momentum to the explosion. The neutrinos provide that potential. Although they interact only weakly with matter, the sheer quantity emitted an immense fraction of the star's gravitational energy, means that even a small absorption rate can deliver powerful heating. As neutrinos stream outward from the proto-neutron star, they deposit energy in the dense layers immediately behind the stalled shock. Gradually, this region becomes a zone of heating known as the gain layer, where the temperature rises as energy accumulates. Convection begins driving bubbles of hot gas upward and mixing cooler material downward. These fluid motions, along with the sustained neutrino heating, will soon determine whether the shock revives or collapses inward permanently. Within these few seconds, the entire star undergoes a transformation that determines its future. The energy trapped within the core remains immense, yet only a tiny fraction will ever reach the surface. The rest radiates invisibly as neutrinos, carrying away the memory of collapse. In total, these particles remove more than 90% of the energy released by the event. They stream through layers of dense matter, escaping into interstellar space where their faint traces might one day be detected. For now, the proto-neutron star remains hidden, surrounded by layers of infalling gas and a shock front struggling to push outward. Inward of the shock, the pressure waves and neutrino flux create an environment of extraordinary complexity. Magnetic fields begin to intensify as turbulence stirs the conducting plasma. Rotation inherited from the original star concentrates energy along the rotational axis. In some models, these effects may drive powerful jets that pierce through the overlying material, shaping the geometry of the eventual explosion. Yet in most cases, the process remains spherically symmetric, governed primarily by neutrino heating. The core trembles in quasi-stable oscillations, absorbing and releasing energy in rapid cycles, until one final surge of neutrino pressure tips the balance. Throughout this time, the outer layers still appear motionless to a distant observer. Light requires minutes to cross the radius of the star, while the inner transformation unfolds in milliseconds. The disconnect between surface calm and interior chaos creates a deceptive stillness. Soon, however, the shock will break free and the energy stored within the core will erupt through the star's envelope. The moment of core collapse will end, giving rise to the explosion that scatters the outer layers into space and leaves behind the dense heart that will become a neutron star. The collapse itself, though brief, marks one of the most extreme transitions known in the universe. From fusion-supported equilibrium to degenerate matter, from atomic order to neutron fluid, the change occurs under absolute control of physical law. No external force guides it. Gravity and quantum mechanics alone dictate the outcome. Within a single second, the core's identity shifts from stellar material to the seed of a new object invisible and compact beyond comprehension. This is the moment when a star's life ends, and another form begins, when the heat of creation turns inward, and matter folds into the smallest space nature allows. At the exact center of the imploding star, the collapse halts against the resistance of nuclear matter. In less than a heartbeat, the core reaches densities beyond what atomic structure can sustain. Nuclei dissolve, neutrons press against one another, and the force that binds matter at the subatomic scale rises to stop further compression. When the infalling layers strike this incompressible surface, they rebound. The collision creates a shock wave that races outward through the inner regions of the collapsing core. It is a boundary between two extremes: inward-moving material, falling at a fraction of the speed of light, and an outward-moving front of compressed matter, heated to extraordinary temperatures. For an instant, gravity and pressure meet in balance, then separate, releasing a pulse of kinetic energy that spreads through the star's interior. The shock front is the first outward signal of the coming explosion. This new wave travels into a hostile environment. The density above the core remains enormous, and in falling material continues to pour downward. The shock pushes outward through gas that is itself moving inward, forcing it to slow, compress and heat. Behind the shock lies a layer of dense shocked matter. Ahead of it, layers of stellar material collapse freely toward the center. Temperatures behind the shock reach tens of billions of degrees Celsius, hot enough to break atomic nuclei apart into free nucleons. Photons cannot escape, and even neutrinos struggle to pass through the thick opaque layers. The entire region becomes a cauldron of radiation, and nuclear fragments sealed inside the dying star. As the shock expands, it faces continuous opposition from gravity and from the relentless inflow of matter above it. Every layer the shock encounters adds to its burden. Each newly shocked region must be heated and accelerated outward, consuming the energy of the front itself. At first, the rebound energy from the collapsing core sustains this motion. But within milliseconds, the shock begins to lose power. Energy is drained as the shock dissociates atomic nuclei into their components. The conversion of heavy nuclei into free neutrons and protons consumes a vast fraction of the available energy. At the same time, neutrinos generated in these reactions escape, carrying away more energy and cooling the region behind the shock. What began as a powerful surge slow stalls and then holds position tens of kilometers above the core. This stalled shock is a delicate structure. On one side lies the dense proto-neutron star radiating neutrinos. On the other side, a stream of infalling gas continues its collapse. Between them, the shock front marks a temporary equilibrium. For the explosion to succeed, this frontier must somehow gain new energy. For now, it flickers in place, balanced between outward pressure and the overwhelming weight of the infalling envelope. The next few hundred milliseconds will decide whether the event becomes a full supernova or collapses further toward a black hole. Beneath the shock, the proto-neutron star continues to form. It is small, only a few tens of kilometers across, but it contains more mass than the Sun. Its density is so high that a teaspoon of its material would weigh billions of tons. The inner core stabilizes through neutron degeneracy pressure, while the outer layers remain fluid, turbulent, and intensely hot. Convection begins within the outer mantle, as heat flows outward from the interior. These convective motions stir the surrounding material, transporting energy toward the stalled shock and mixing the matter that will later form the neutron star's crust. Magnetic fields strengthen as turbulence stretches and folds lines of flux within the electrically conducting plasma. Rotation further distorts these fields, twisting them into helical structures that thread through the dense matter. The combined effects of convection, rotation, and magnetism begin to shape the energy distribution that will soon decide the fate of the shock. The neutrinos escaping from the core now dominate the dynamics of this inner region. Produced in enormous quantities by the conversion of protons to neutrons, they carry away the majority of the gravitational energy released by collapse. Yet the layers just above the core remain dense enough to absorb a fraction of this flux. The absorption of neutrinos deposits heat into the material behind the shock, raising its temperature and pressure. This process, though inefficient, occurs over a vast area and with immense flux. Gradually it begins to re-energize the shock's base. The heated material expands, reducing the infall rate locally and creating convective plumes that push upward. These motions disturb the symmetry of the system, producing ripples and oscillations that can help the shock regain strength. Meanwhile, above the shock, the star continues to fall inward. The envelope that once spanned millions of kilometers now compresses toward the core. The outer layers, moving at supersonic speeds, pile up against the stalled front. Pressure builds and the region becomes unstable. The combined action of neutrino heating, convection, and fluid instabilities produces an environment of immense turbulence. Rising hot bubbles push outward, while cooler streams sink toward the core, carrying fresh material into the heating zone. This feedback strengthens the local energy deposition, sustaining the convective motion and increasing the chance of a full revival. As the seconds pass, the dynamics remain finely balanced. The shock may either resume its outward expansion or collapse inward once more. In many simulations, the balance tips when neutrino heating overtakes the energy losses from dissociation and radiation. The stalled front suddenly accelerates outward again, driven by pressure from below and reduced infall from above. The material behind it expands rapidly, cooling and recombining into heavier nuclei. The process releases further energy, amplifying the shock's power. Within moments, the front becomes a true explosion, racing through the star's remaining layers. The initial failure of the shock gives way to renewal, transforming the collapsing star into an expanding supernova. In this brief but decisive interval, the universe witnesses the creation of new heavy elements. As the shock moves outward, it passes through layers rich in silicon oxygen and carbon, igniting explosive nuclear reactions that synthesize elements heavier than iron. These products will later drift into space, forming the raw material for new stars and planets. The explosion is not uniform. Variations in density and composition create asymmetries that will echo through the expanding debris. At the center, the compact remnant stabilizes as the proto-neutron star cools and contracts. If the shock fails, instead, the outcome changes drastically. The continued infall of material can overwhelm the core, driving it beyond the maximum mass that neutron degeneracy can support. In that case, collapse resumes and the remnant becomes a black hole. But when conditions align, when neutrino heating, convection, and magnetic fields combine effectively, the shock survives and grows. The core remains intact, forming a neutron star that will radiate its residual heat for millions of years. In the silent aftermath of collapse, the shock front marks the transition between death and survival. It is a moment measured in fractions of a second, yet carrying the outcome of the star's entire history. The energy released within the shock, the heating provided by neutrinos, and the turbulent interplay of matter and radiation all converge to determine what remains after the blast. Whether the result is a brilliant supernova or a hidden collapse, the shock's birth and evolution define the boundary between one form of existence and another. From this frontier, the first signs of outward life emerge in a star that has already died. The outward surge that begins at the heart of the dying star faces immediate resistance. The shock front born from the rebound of the compressed core expands only briefly before the crushing weight of infalling matter slows it to a crawl. The collapse of the outer layers continues unabated, pouring mass onto the region just behind the shock. Every second brings more material to absorb, more energy to consume, and more gravitational pressure to overcome. The energy released by the rebound, immense but finite, cannot carry the shock through the enormous envelope above it. As the shock moves outward, it loses its initial strength to three powerful drains: the dissociation of heavy nuclei, the emission of neutrinos, and the relentless inward pull of gravity. It becomes a fragile boundary suspended between momentum and failure. Within milliseconds, the energy that once seemed boundless has been largely spent. Each nucleus that passes through the shock breaks apart into free neutrons and protons, consuming millions of electron volts per atom. This invisible expenditure bleeds the wave of its vitality. The dissociated matter piles up behind the shock, forming a dense hot shell of free nucleons and radiation. Above it, new layers of the collapsing star continue to fall inward at high velocity, compressing the region further. The competition between inflow and rebound stabilizes the shock in place. It stalls at a distance of about 150 kilometers from the center, neither advancing nor retreating, trapped within a state of tenuous equilibrium. Beneath this frozen boundary, the proto-neutron star radiates energy in the form of neutrinos. These ghostly particles are produced in staggering numbers as neutrons and protons exchange identity through weak nuclear reactions. They escape in all directions, carrying with them the heat and energy of the dense core. Over a period of seconds, they remove the majority of the gravitational energy released during collapse, yet not all of them escape freely. The region just below the shock is thick enough that a small fraction of the neutrinos are absorbed. That absorption transfers energy to the matter there, heating it and raising its pressure. This process, though subtle, becomes the seed of revival. At the same time, convection begins to stir the hot mantle between the proto-neutron star and the stalled shock. In this turbulent zone, rising bubbles of heated gas carry energy outward, while cooler matter falls inward, bringing fresh material into the heating region. The circulation enhances the effectiveness of neutrino absorption as newly exposed material continues to gain energy, while cooler gas is reheated upon descent. The resulting pattern resembles a rolling ocean of plasma with buoyant plumes pushing toward the shock front. The effect is slow and cumulative, but it marks the beginning of the shock's struggle for survival. The balance between collapse and explosion is delicate. Too little neutrino heating and the wave will fade, completely collapsing back toward the core. Too much accretion, and the weight of falling matter will smother any outward motion. The shock survives only by maintaining a narrow window of conditions sufficient: heating, moderate infall, and sustained convection. Every parameter matters. The rotation of the core adds a new dimension to this balance. If the collapsing star possessed even modest spin before collapse, angular momentum now concentrates in the small radius of the proto-neutron star, creating enormous rotational energy. That energy can twist magnetic fields, driving them into complex patterns that interact with the surrounding plasma. The fields may channel energy along the rotational axis, forming narrow jets of motion that help pierce the overlying layers. The outcome depends on the symmetry of the system, the distribution of angular momentum, and the precise timing of neutrino energy deposition. In most cases, the stalling phase lasts less than 1 second. During that short interval, the structure of the entire star is decided. Neutrino heating continues to deposit energy in the region just behind the shock, creating a pressure gradient that slowly strengthens. Convective motions grow more vigorous, amplifying turbulence and transporting heat. The density of the infalling material gradually declines as the outer shells of the star begin to reach the core. When the rate of infall drops enough, the shock begins to respond. It trembles, then oscillates, driven by rising bubbles of hot gas. In some directions it moves slightly outward, in others it retreats. The symmetry breaks, and the front begins to slosh, an early sign that motion is returning. This oscillatory phase can trigger a runaway effect. Each outward pulse allows heated matter to expand, reducing its density and enhancing further absorption of neutrinos. The stronger the heating, the faster the expansion, and the more neutrinos the gas can capture. This positive feedback accelerates the process until the shock gains enough energy to move steadily outward. Once this threshold is crossed, the balance shifts decisively. The previously infalling matter now slows, halts, and reverses direction. The shock begins its true expansion, and the star's outer layers are finally driven outward. For the shock to survive, however, more is required than energy. The structure of the star itself plays a crucial role. The density profile of the collapsing envelope determines how much mass must be moved at each radius. A steep decline in density with radius favors expansion. A shallow one resists it. The composition also matters, for layers rich in oxygen and silicon absorb shock energy differently than those dominated by lighter elements. Each composition boundary the shock encounters changes its momentum, sometimes accelerating it, sometimes damping it. The interplay of these layers gives the explosion its characteristic asymmetries and shapes, the final distribution of ejected material. In some cases, the outward moving front becomes distorted by large-scale instabilities. Plumes of hot material rise along some directions, while cooler, denser gas continues to accrete along others. The resulting flow resembles a vast churning storm. These instabilities may even seed rotation in the newly forming neutron star, imparting kicks that can propel it through space at hundreds of kilometers per second. The violence of these internal motions contrasts with the external appearance of stillness. For many seconds after collapse, the star's surface remains unchanged, its outermost layers yet to feel the effects of the explosion developing within. Eventually, the shock achieves full independence from the infalling gas. The heating behind it outpaces all cooling losses, and the momentum carried outward becomes irreversible. The expanding front begins to travel through the remaining layers of the star, triggering nuclear reactions that synthesize new elements. Within seconds, the wave will reach the surface and release a flash of light that will later be seen across galaxies. But inside, the proto-neutron star remains enveloped in its own dense cocoon, cooling by neutrino emission and contracting into a smaller, more stable object. The shock's survival ensures that the core will remain intact as a neutron star rather than collapsing into a black hole. The struggle of the shock is therefore the star's final contest between collapse and rebirth. Its success means that matter once bound in the heart of a giant will scatter across space to enrich the universe with heavy elements. Its failure means total absorption, the creation of an invisible singularity. The balance between these outcomes depends entirely on the physics of a few seconds within a sphere only hundreds of kilometers wide. In that brief and narrow space, gravity and quantum forces decide the course of stellar death. The stalled shock, once near failure, becomes either the engine of an explosion or the mark of complete collapse. Its endurance defines whether light returns to the sky or vanishes forever into darkness. Inside, the collapsed core energy now flows in a form almost invisible to the universe. Neutrinos produced by countless reactions among protons, neutrons and electrons stream outward in numbers so great that they carry away most of the gravitational energy liberated by the collapse. The proto-neutron star, still less than 30 kilometers across, becomes the brightest known neutrino source in the cosmos. In the first second after core bounce, this emission dominates all other forms of radiation combined. Photons cannot escape the opaque material, but neutrinos weakly interacting with matter pass through it, diffusing outward from layers where densities reach 1,000,000,000,000 times that of water. Each particle travels at nearly the speed of light, borne in a storm of reactions that trace the core's cooling and contraction. The interior temperature exceeds tens of billions of degrees Celsius. Under these conditions, the exchange of energy through ordinary matter becomes impossible. Instead, neutrino diffusion becomes the only efficient pathway for cooling. The proto-neutron star acts as a reservoir of trapped radiation, its outer layers dense enough to scatter neutrinos repeatedly before they escape. This region, known as the neutrinosphere, lies at the boundary between opacity and transparency for these particles. From there, a continuous flood streams outward in every direction, carrying information about the temperature composition and density of the inner star. The flux peaks within seconds, releasing more energy than a typical galaxy radiates in the same time. Yet despite their abundance, neutrinos rarely interact with the matter outside. only a tiny fraction of them deposit heat in the layers behind the stalled shock. But that fraction is enough to determine the outcome of the explosion. Each absorption converts part of the neutrino's energy into thermal motion, of particles slowly raising the pressure behind the shock front. This heating, though, spread over a region only a few hundred kilometers thick, begins to re-energize the stalled wave. The delicate interplay between neutrino emission diffusion and absorption defines this brief and decisive phase. The processes that generate neutrinos are numerous. In the dense core beta interactions dominate where protons capture electrons to form neutrons and release electron-type neutrinos. At the same time, inverse reactions occur as neutrinos convert neutrons back into protons. Thermal pair production adds more as electron-positron annihilation spawns neutrino-anti-neutrino pairs of all flavors. These reactions occur continuously, maintaining a dense sea of particles that scatter and exchange energy until they finally escape. The balance among these reactions sets the temperature and chemical composition of the outer mantle. As the proto-neutron star cools, the spectrum of emitted neutrinos evolves. Early on, they carry tens of millions of electron volts per particle, a measure of the extreme heat near the core. Over seconds, the temperature falls and the flux gradually declines. However, the total energy released remains staggering, about 10 to the power of 46 joules, almost all of it in neutrinos. Only a small remainder, less than 1%, powers the visible supernova. This imbalance highlights the efficiency of neutrino cooling and the inefficiency of light in such dense environments. The diffusion of neutrinos also shapes the structure of the forming star. As energy leaves the inner regions, the pressure drops and the core contracts further. Each contraction increases density and drives new reactions that release even more neutrinos, establishing a feedback that accelerates cooling. The outer layers respond with turbulent convection, carrying heat outward and mixing matter enriched by earlier reactions. In these layers, neutrons and protons combine to form light nuclei, releasing bursts of radiation that accompany the escaping neutrinos. The result is a dynamic layered flow of particles and energy, each zone defined by its opacity and reaction rate. Outside the neutrinosphere, where densities fall below critical thresholds, the escaping particles continue almost freely. They traverse the surrounding envelope with minimal scattering, effectively invisible to the collapsing gas. Yet their presence is profound. The momentum they transfer, though minute, provides pressure that contributes to the revival of the stalled shock. This mechanism, known as neutrino heating, becomes the bridge between core physics and the outer explosion. The heating rate depends on the neutrino luminosity and the density of absorbing material. When these align optimally, the energy deposition ignites large convective motions that help propel the shock outward. As seconds pass, the core settles into a quasi-steady state of emission. The neutrino flux diminishes gradually, but the distribution remains anisotropic due to convection and rotation. In some directions, outflow is enhanced. In others, it weakens. These asymmetries, though small, can imprint on the motion of the newborn neutron star, giving it a recoil velocity that will later propel it through space. The directionality of neutrino emission also affects the shape of the explosion, imprinting subtle asymmetries that later become visible in the expanding supernova remnant. Meanwhile, the outer regions of the proto-neutron star continue to evolve chemically. The heat from neutrino interactions drives nucleosynthesis in the neutrino-driven wind, an outward flow of matter that carries newly formed nuclei away from the surface. This wind emerges once the shock has moved far enough outward to reduce pressure confinement. For now, though, the heating remains trapped behind the stalled front, accumulating energy. The contest between accretion and heating continues, each neutrino captured, bringing the explosion closer to revival. Within the first 10 seconds, the neutrino luminosity declines by orders of magnitude as the star cools. The interior, once fluid and turbulent, begins to stabilize. Degeneracy pressure of neutrons becomes the dominant support against gravity. The mantle contracts, the radius shrinks, and the neutrino flux hardens briefly before fading. This cooling defines the transition from a proto-neutron star to a mature neutron star. By the end of this period, most of the energy of formation has escaped, leaving behind a dense cold remnant with magnetic fields frozen into its structure. For an observer at immense distance, these events are silent. Only the neutrinos themselves carry direct evidence of the collapse arriving at Earth as a faint brief pulse lasting a few seconds. In 1987, detectors recorded such a signal from a supernova in the Large Magellanic Cloud, confirming the theoretical predictions of this process. From that rare detection, astronomers inferred the timing, energy, and cooling rate of a real neutron star's birth. The observation showed that almost the entire gravitational energy of the collapse indeed emerged as neutrinos invisible, yet overwhelmingly dominant. In the core, the last phases of intense neutrino emission mark the transition to a new stability. The shock has now received sufficient heating to resume motion. The balance tips and outward acceleration resumes. As the wave expands through the stellar mantle, it carries with it the legacy of these neutrinos, the invisible hand that lifted the remnant from failure to explosion. The proto-neutron star contracts quietly behind the departing shock, radiating the last traces of its trapped energy. Its surface temperature continues to drop, its emission fades, and its structure begins to crystallize. The era of blinding neutrino light closes, leaving only a newborn neutron star surrounded by expanding debris. In the depths of that fading brightness, one of the universe's densest and most enduring objects has emerged from the death of a star. After the intense flood of neutrinos has swept outward from the collapsing core, the fate of the star still hangs in the balance. The shock front remains stalled, hovering in the inner mantle like a flickering shell of potential energy. The proto-neutron star beneath it radiates continuously, flooding the surrounding matter with neutrinos of extraordinary luminosity. In these invisible waves lies the last hope for revival. As they stream through the dense gas behind the shock, a fraction are absorbed, depositing heat in the region that had been frozen between expansion and collapse. The interaction of these particles with free protons and neutrons injects thermal energy into the matter, driving convection and gradually lifting the weight of the overlying layers. The process is subtle but cumulative, and over the span of a second the stagnation begins to change. The dying shock starts to breathe again. At first the effect is imperceptible. The stalled wave trembles as buoyant pockets of hot material rise through cooler surroundings. Convection becomes increasingly vigorous, producing a roiling pattern of circulation that transports heat outward. The energy deposited by neutrinos no longer dissipates immediately. It builds within these rising plumes. The heated regions expand, pushing on the shock front and causing it to oscillate. The system enters a phase of large-scale instability, known as the standing accretion shock instability. Waves of motion travel through the entire structure, amplifying asymmetries and helping the shock to regain momentum. Each oscillation allows more energy to accumulate behind the front, slowly tipping the balance in favor of expansion. Rotation and magnetic fields now play their part. The proto-neutron star spins rapidly, its rotation period measured in milliseconds. This spin twists magnetic field lines anchored in the conducting plasma, winding them into tight spirals that trap and channel energy. Magnetic tension combined with differential rotation concentrates power along the rotational axis. In some stars, this effect creates jets that tunnel through the surrounding matter, adding mechanical force to the neutrino-driven push. Even when no jets form, the interaction of rotation and magnetism redistributes angular momentum, making the heating more efficient and stabilizing the outward motion. These internal dynamics, invisible to the eye, shape the explosion's geometry and determine whether it remains roughly spherical or develops elongated lobes that pierce through the envelope. As the seconds pass, conditions approach a tipping point. The neutrino heating behind the shock exceeds the cooling losses from radiation and nuclear dissociation. The material in this gain region expands faster than it can be replenished by infalling gas. Pressure increases and the front begins to move outward steadily. The long stalemate ends. The revival of the shock is not sudden but continuous, a smooth acceleration that transforms the internal motions of plasma into coherent expansion. The outer layers still collapsing from above meet this reversal with resistance, but their momentum is already failing. The heating and turbulence below act as a sustained engine converting neutrino energy into kinetic motion. When the shock finally breaks free, it travels through the stratified layers of the star, each with its own composition and density. The wave accelerates through regions of decreasing density, igniting explosive burning in shells of silicon and oxygen. Temperatures rise above 5 billion degrees Celsius, sufficient for nuclear fusion to resume briefly. New elements form in fractions of a second: iron-nickel, cobalt and heavier nuclei enriching the matter that will soon be expelled into space. The revival transforms a dying collapse into an expanding sphere of nuclear fire. What began as an invisible struggle within a few hundred kilometers of the core now extends across millions. During this phase, the balance of forces remains delicate. The shock's expansion is driven by energy deposited long before it becomes visible. The neutrinos continue to flow from the proto-neutron star, but their influence weakens with distance. What sustains the motion now is the thermal energy stored in the heated mantle and the mechanical work done by convection and magnetic pressure. These forces must overcome both gravity and the inertia of the overlying layers. In the densest stars, where the outer shells contain several solar masses, the explosion may remain marginal. If it falters, fall back. Accretion can drain the energy and lead to renewed collapse. If it persists, the core remains intact, destined to become a neutron star. In the region immediately behind the expanding shock, conditions shift rapidly. The gas cools and recombines as it expands, releasing additional energy that further accelerates the outward flow. The density drops, the temperature falls, and the opacity decreases. Radiation begins to leak outward, and the shock front transitions from a purely mechanical wave into a radiative one. Light trapped for so long within the star starts its journey to the surface. The transition marks the birth of the visible supernova. Yet at this stage, the proto-neutron star still lies hidden, radiating neutrinos and contracting into a more compact configuration. Its radius shrinks, its surface temperature declines, and its rotation continues to accelerate as angular momentum is conserved. The revival of the explosion also sets in motion the ejection of the star's outer layers. Material that once lay stable in gravitational balance is now swept up by the expanding shock and hurled outward into space. The energy released, about 100 trillion joules, is enough to unbind the entire star. The outer envelope, travelling at thousands of kilometers per second, carries with it the newly forged elements that will later enrich interstellar clouds. The light from this explosion, delayed by the time it takes for the shock to reach the surface, will soon illuminate the cosmos, visible for weeks or months before fading. deep within the proto-neutron star continues to evolve. It is now the remnant of collapse, dense beyond ordinary comprehension, but still cooling through neutrino emission. Its surface layers convect slowly as residual heat escapes. The magnetic fields amplified by differential rotation become locked into the star's structure, freezing patterns that will later define its behavior as a pulsar or magnetar. The interior settles toward equilibrium, supported entirely by neutron degeneracy pressure. The energy released during this transformation is enormous, but the system now enters a period of calm compared to the preceding chaos. The shock's revival has sealed its fate. The object will survive not as a black hole, but as a neutron star. The star's death is now an outward-moving event, no longer a collapse, but an eruption. Each shell the shock encounters adds new complexity to the expanding debris. As the outer envelope detaches, the internal layers mix, producing swirling vortices and filaments that will persist for thousands of years in the supernova remnant. The symmetry of the explosion may be broken, leaving knots of denser matter and cavities of thinner gas. Through these openings, radiation escapes, marking the beginning of the visible phase of the supernova. In a distant galaxy, this light will appear suddenly, where before there was only darkness, a single point shining brighter than a billion suns. The revival of the explosion thus completes the transformation from gravitational implosion to cosmic expansion. Neutrinos, silent carriers of energy, have achieved what photons could not. They have rescued the star from total collapse. The energy they delivered, though small compared to the total emitted, was sufficient to tip the balance. The shock once stalled and dying has become a wave of creation. The proto-neutron star at the center now rests within a growing cavity of emptying space surrounded by gas moving ever outward. The visible light of the supernova will fade in time, but the compact core will endure. The process has given birth to one of nature's most extraordinary objects, a neutron star forged in the last heartbeat of a dying sun, born from the silent force of neutrinos. Once the revived shock front escapes the gravitational choke of the inner star, its outward march becomes unstoppable. It plows through the dense stratified layers that once surrounded the core, converting collapse into expansion. The materials within these layers, silicon, oxygen, carbon, and lighter elements, are heated to fusion temperatures as the wave passes. In less than a second, nuclear reactions reignite in shells, where the heat briefly exceeds billions of degrees Celsius. Heavy nuclei are synthesized, and matter that had remained unchanged for millions of years transforms into new elements. The outward-moving shock drives an expanding sea of radiation and gas that tears through the star's body. For the first time since the collapse began, motion reverses entirely. The star's death becomes a dispersal. In the inner regions, the pressure remains extreme, but energy now flows outward instead of inward. The mantle once falling begins to lift. The layers that formed over the star's long lifetime peel away one by one. The mass of the ejected envelope depends on the original star's size, but the process is violent in every case. The shock front accelerates as it moves outward into decreasing density. The energy transferred from the core's neutrino-driven heat becomes kinetic energy, propelling billions of tons of matter into space at thousands of kilometers per second. The outward momentum is uneven, sculpted by turbulence rotation, and magnetic fields frozen into the gas. In some directions, the expansion is faster, forming lobes that will later give the remnant its asymmetrical shape. The first few seconds after breakout are the most destructive. As the wave encounters new shells, each composed of different elements, the density and temperature change sharply. In the silicon-rich layer, explosive burning continues, forging nickel and iron. When the front reaches the oxygen and carbon zones, fusion resumes there as well. producing calcium, sulfur, and magnesium. The sequence of reactions releases fresh bursts of energy that add to the shock's power. The star becomes an enormous nuclear reactor in reverse converting structure into debris. The fusion ceases as the temperature drops behind the expanding front, but its products remain mixed into the outflowing material. These elements will later cool and condense into grains of dust and the seeds of future worlds. As the envelope expands, it begins to detach completely from the core. The mass that once enclosed the proto-neutron star loses its gravitational bond. What remains behind is a compact remnant surrounded by a growing cavity of hot diffuse gas. Radiation trapped within the ejector starts to diffuse outward. When the optical depth falls low enough, light finally escapes. The moment marks the emergence of the supernova's visible phase. To an observer far away, the star brightens, suddenly reaching a luminosity that can exceed that of an entire galaxy. This visible glow, lasting days or weeks, is powered not directly by the explosion itself, but by the decay of radioactive nuclei, mainly nickel-56 and cobalt-56 formed during the ejection. As these unstable isotopes transform into iron, they release gamma rays that heat the surrounding gas and sustain the brightness long after the initial flash has passed. Within the expanding debris, the velocity distribution freezes in place. Inner regions move more slowly while outer shells accelerate ahead. The front continues to push outward until it meets the interface, where the stellar wind of the original star merges with the interstellar medium. This boundary marks the edge of the emerging supernova remnant. The shock slows as it sweeps up external gas, converting kinetic energy into radiation. Over time, the remnant will cool and expand further, forming a glowing shell of ionized gas visible for thousands of years. Inside that shell, the neutron star will remain hidden for a while by dense clouds of dust and debris, its own emission faint but enduring. The physics of this envelope ejection carries immense importance beyond the death of the star itself. It disperses the heavy elements necessary for planets, atmospheres, and biological chemistry. Every atom of iron, calcium, and gold once forged in these violent moments now drifts through galaxies, waiting to be incorporated into new generations of stars. The ejection is not only an end, but also the mechanism by which the universe enriches itself. The same process that destroys one star becomes the source of building blocks for countless others. The structure of the ejected material reflects the complexity of the forces that shaped it. The expanding gas is neither smooth nor uniform. Pockets of different compositions mix turbulently, creating filaments and knots. Magnetic fields thread through these structures, guiding charged particles and influencing the emission of radiation. Over months and years, the ejector cool, forming molecular species that will eventually condense into dust grains. These grains absorb and scatter light, obscuring the core from view, but later glowing in infrared radiation detectable across interstellar distances. In a few hundred years, the remnant will evolve into a nebula, illuminated by the faint radiation of the central neutron star or pulsar. During the first few hours after the explosion, the inner regions continue to exchange energy with the core. Some fraction of the ejected material does not achieve escape velocity and begins to fall back under gravity. This fallback accretion can alter the final mass of the neutron star, or in extreme cases cause delayed collapse into a black hole. But when the explosion is sufficiently strong, the returning matter remains minimal. The outer envelope, now far beyond gravitational reach, expands freely into the void. The velocity field stabilizes and the debris continues its journey outward at thousands of kilometers per second, its density decreasing exponentially with time. By now, the proto-neutron star at the center has cooled significantly. Its neutrino luminosity declines as the interior settles into thermal equilibrium. The outer layers solidify, forming the beginnings of a crust composed of atomic nuclei arranged in crystalline structure. The transition from fluid to solid happens gradually layer by layer, while the magnetic fields generated during the explosion become trapped within the crust. These frozen fields will later govern the star's electromagnetic behavior. For now, however, the new star remains shrouded in darkness, hidden within the expanding veil of gas it created. In distant galaxies, similar explosions occur every century or so, each one enriching space with heavy elements. The aftermaths visible as bright nebulae are silent records of their origins. Their filaments carry traces of the elements produced while at the center a single compact star spins silently. The energy of the envelope's ejection, though, released in a moment, leaves effects that persist for millions of years. The interstellar medium becomes seeded with material that will one day condense again into new systems. The cycle of creation and destruction continues, governed by the same laws that now hold the newly formed neutron star in equilibrium. The ejection of the stellar envelope completes the visible death of the massive star. From here onward, the remnants' evolution will unfold in quiet stages governed by cooling magnetic fields and slow contraction. The explosive moment has passed, but the consequences of that event ripple outward for eternity. Every glowing remnant seen in the night sky is a witness to this process, a fossil of energy release that once began deep within a collapsing core. Beneath those luminous shells lies the compact object that survived dense beyond imagination, the neutron star born when the last light of the star's life turned into the first darkness of its new form. At the center of the expanding debris, far beneath the glowing layers of the ejected envelope, a new kind of star takes shape. What remains of the collapsed core is neither ordinary matter nor anything the universe had seen before the first supernovae occurred billions of years ago. The proto-neutron star is a compact sphere of nuclear density, a remnant formed from the ruins of atomic structure. Its radius measures only a few tens of kilometers, yet its mass equals that of the Sun. Within this sphere, gravity and quantum pressure have reached a balance that halts further collapse. Every atom that once composed the core has been stripped to its fundamental particles. Electrons and protons have fused into neutrons through weak nuclear reactions, and what endures is a fluid of degenerate matter held together by the most powerful forces in nature. The newborn object glows with internal heat that defies comprehension. Temperatures exceed 10 billion degrees Celsius, and the pressure at its center rises beyond any scale familiar to physics outside the atomic nucleus. The outer layers churn with convective motion as the star cools, radiating neutrinos that carry energy away into space. These particles, weakly interacting yet abundant, dominate the transport of energy, allowing the proto-neutron star to contract and settle. Over the course of seconds, the sphere loses a large fraction of its thermal energy in an invisible storm of radiation. The light that once defined the parent star has gone replaced by a flux of particles that can pass through entire worlds without obstruction. The internal structure of this new body is unlike anything found elsewhere. The density gradient from surface to center is steep. The outer regions, known as the mantle, remain semi-transparent to neutrinos and less degenerate, while the deeper interior approaches uniform nuclear density. Matter there behaves as a liquid of neutrons with a small fraction of protons and electrons mixed within. Pressure is provided by the degeneracy of neutrons, a quantum mechanical effect that resists further compression even under gravity's overwhelming pull. This degeneracy pressure is the final defense against collapse. Were the mass of the core only slightly greater, even this force would fail, and the result would be a black hole. But for now, the balance holds. The proto-neutron star exists on the narrow threshold between persistence and oblivion. The surface of the remnant is not solid. It is a fluid boundary where density drops sharply and neutrinos escape into the surrounding space. The temperature there is so high that atomic nuclei cannot survive. Instead, the outermost layer consists of a thin atmosphere of free nucleons and leptons seething with radiation. As the star cools, this boundary contracts and the neutrino luminosity gradually diminishes. The process resembles a prolonged exhalation of energy that began at the moment of core bounce and continues as the remnant stabilizes. Over tens of seconds, the heat trapped in the dense interior leaks outward through diffusion, while the neutrino flux carries it away. Magnetic fields amplified during collapse now thread the entire structure. The rapid rotation inherited from the progenitor star winds these fields into immense loops that pierce the surface and extend into the surrounding plasma. The strength of these magnetic fields can reach trillions of times that of Earth, locking the outer fluid into rigid rotation. This magnetic scaffolding will later govern the remnant's behavior, channeling charged particles and generating radiation as the star spins. For now, the fields remain submerged within the dense plasma, frozen into the fluid but dormant. Within the first minute, the proto-neutron star transitions through dramatic physical changes. As the temperature drops, neutrons begin to pair, forming the first signs of superfluidity within the deeper layers. The outer mantle, still turbulent, gradually settles as convection subsides. The surface shrinks, the rotation rate increases due to conservation of angular momentum, and the magnetic fields grow more concentrated. The star's moment of birth ends with quiet contraction rather than explosion. Around it, the supernova ejecta expand outward into space, their light brightening and fading in cycles powered by radioactive decay. But within the central remnant, a steady cooling replaces the chaos that created it. Even as the proto-neutron star contracts, some material from the outer layers continues to fall inward. The fullback accretion phase delivers additional mass and angular momentum to the remnant. When these fragments strike the surface, they release bursts of heat and radiation, briefly re-energizing the emission of neutrinos. The added mass may change the star's structure, potentially pushing it closer to the stability limit that divides neutron stars from black holes. In most cases, the accretion ends before that boundary is reached, and the remnant stabilizes as a neutron star with a mass between 1 and 2 times that of the Sun. From the perspective of energy, the birth of the proto-neutron star marks the conversion of gravitational potential into thermal and neutrino energy. The collapse has compressed ordinary matter by a factor of billions, and the resulting release of binding energy is among the most efficient processes known. Nearly all of that energy leaves in the form of neutrinos. Only a small residue remains as heat and rotational energy in the star itself. The efficiency of this conversion determines how bright and long-lived the subsequent supernova will appear, for the outer explosion depends on the core's ability to shed energy outward. Over the next several tens of seconds, the proto-neutron star becomes less luminous in neutrinos, as its internal temperature falls below a few billion degrees Celsius. The atmosphere contracts and cools enough for light nuclei to form near the surface. The emission shifts toward lower energies, marking the end of the active neutrino phase. The object has now entered the earlier stage of a stable neutron star. From this point onward, its evolution slows drastically. Cooling will continue for thousands of years, but most of the internal structure has already been set. The transition from collapse to stability is absolute yet invisible. To distant observers, no light escapes from the newborn star, only the faint residue of neutrino emission. The expanding supernova cloud hides it entirely. But within that obscured core, the universe has gained a new kind of body, compact, dense and enduring. In a few hundred years, when the surrounding gas becomes transparent, the neutron star's own emission will emerge. Rotational energy stored in its rapid spin and magnetic field will then power beams of radiation that sweep through space. Astronomers will later call these objects pulsars, but in this first moment it is simply a hot, cooling remnant, resting in the vacuum created by its own explosion. The birth of the proto-neutron star concludes the violent sequence that began with the collapse of an iron core. In less than a minute, a stellar interior has transformed into one of the densest objects in existence. The process unites the extremes of physics, quantum degeneracy, relativity, nuclear forces, and magnetic turbulence within a single small sphere. The light of the supernova may fade, but the remnant will persist for billions of years, carrying within it the memory of the collapse that made it. Around it, the expanding debris continues to cool, forming a nebula that will shine for millennia. Within that silent core lies matter so dense that it challenges the limits of comprehension, a proto-neutron star born from gravity's victory and stabilized by the last pressure nature can provide. As the proto-neutron star settles from its violent birth, a faint but persistent outflow begins to emerge from its surface. This flow, powered not by fusion or magnetism, but by the steady emission of neutrinos, becomes one of the final expressions of the supernova's internal energy. The neutrinos escaping the dense interior interact with the thin atmosphere of nucleons that clings to the star's surface. Each absorption imparts a minute push, and though the effect on any single particle is small, the combined influence of countless neutrino interactions drives a continuous wind of matter away from the star. This neutrino-driven wind carries the last remnants of heat and composition from the young remnant into the expanding space left by the explosion. It is faint compared with the supernova's earlier violence, yet it plays an essential role in shaping the chemical legacy of the event. The outflow begins only a few seconds after the shock's revival. By this time, the proto-neutron star has contracted to a radius of about 20 kilometers, and its surface temperature has fallen to a few billion degrees Celsius. The density at the base of the wind remains high, and the gas is composed primarily of neutrons, protons and electrons in rapid motion. As neutrinos stream outward from the inner regions, they deposit energy through weak interactions, heating this outer layer and creating pressure gradients that accelerate material outward. The balance between gravitational attraction and neutrino heating determines the mass loss rate and speed of the wind. Where heating dominates, particles escape. Where gravity prevails, the matter remains bound. In the first few seconds, the wind is dense and fast. Temperatures remain high enough for nuclear reactions to proceed, allowing light elements such as helium, lithium, and heavier isotopes to form. As the wind expands and cools, these nuclei freeze out of equilibrium, preserving the ratios imprinted by the conditions near the star. Over time, as neutrino luminosity decreases, the outflow becomes weaker and less dense. What remains is a slow, thin stream of particles carrying the chemical fingerprints of the proto-neutron star's surface. This wind, though, containing only a small fraction of the star's mass, contributes significantly to the synthesis of rare nuclei that cannot be made elsewhere. The composition of the wind depends sensitively on the balance of neutrino species. Electron neutrinos and their antiparticles interact differently with the matter they encounter, altering the relative number of neutrons and protons in the flow. When electron neutrinos dominate, more neutrons convert to protons, creating conditions favorable for proton-rich isotopes. When the opposite occurs, neutron-rich material forms, potentially producing elements through rapid neutron capture, a process known as the R process. Whether a given explosion achieves this depends on temperature, luminosity, and the neutrino energy spectrum. In some stars, the wind produces only light elements. In others, it may forge some of the heaviest nuclei in the periodic table, such as gold and uranium. The neutrino-driven wind continues for tens of seconds, after the explosion gradually fading as the proto-neutron star cools. The outflow transitions from a supersonic wind to a subsonic breeze as neutrino heating declines. Eventually, gravity reasserts full control and mass loss stops. The surrounding supernova ejecta, moving much faster, sweep up the material expelled earlier, carrying it outward into the expanding nebula. Though the total mass of the wind may be less than 1,000th of a solar mass, its composition and energy help determine the chemical structure of the surrounding remnant. The interaction between the wind and the slower, denser inner ejecta creates a boundary of shocked gas that glows faintly in X-rays and gamma rays. Within the proto-neutron star, the emission of neutrinos remains the dominant form of energy transport. Even as the wind fades, the star continues to radiate neutrinos of all types, cooling over the course of about a minute, to a temperature near 1 billion degrees Celsius. By this time, the surface density has dropped, and the atmosphere begins to solidify into the first crystalline layers of the future crust. The last stages of the wind coincide with the transition from the proto-neutron phase to the stable neutron star phase. The material that once formed a hot convective ocean becomes rigid, and the region of active neutrino heating recedes below the surface. The effects of the wind are not limited to composition. The outflow also carries angular momentum away from the star, altering its rotation rate. In the earliest moments, the proto-neutron star may spin hundreds of times per second, but as the wind extracts energy and momentum, the rotation slows, slightly stabilizing the structure. Magnetic fields anchored in the surface are stretched and twisted by the escaping plasma, producing extended magnetized outflows that later shape the surrounding supernova remnant. In extreme cases where magnetic fields exceed 1,000,000,000 times the strength of Earth's, the wind may become magnetically dominated rather than neutrino-driven, leading to highly collimated jets. These rare configurations may give rise to gamma-ray bursts, the most luminous explosions known. For ordinary supernova, however, the wind remains isotropic and moderate, a quiet finale to the storm. In the larger cosmic context, neutrino-driven winds act as subtle forges of chemical diversity. Each newly formed neutron star enriches its environment with small amounts of freshly made isotopes that cannot originate in ordinary stellar fusion. These trace elements later appear in the atmospheres of stars and planets, testifying to the hidden processes that occurred in their ancestral explosions. Though the winds themselves vanish quickly, their contribution to the evolution of galaxies persists for billions of years. The rare elements they produce become part of the cosmic cycle, recycled into new generations of matter. As time passes, the wind ceases entirely. The neutrino emission weakens until it no longer provides sufficient heating to lift material from the surface. The atmosphere, now cool and thin, collapses inward and freezes into a solid crust. The proto-neutron star has completed its transformation. What remains is a compact, stable neutron star surrounded by an expanding cloud of debris. The neutrino-driven wind, once a bridge between collapse and stability, has ended its task. It has carried the last thermal energy of the explosion outward, ensuring that the interior of the new star can cool without further mass loss. The moment marks a change in rhythm across the remnant. The violent phases of collapse, shock, and outflow are over. The neutron star now enters an era of quiet endurance, radiating slowly through neutrinos and later through magnetic and rotational energy. Its structure is set, its density fixed by quantum pressure, its fields frozen into place. Around it, the expanding ejecta continue to thin, revealing the faint glow of the surrounding nebula. In this stillness, the legacy of the neutrino-driven wind endures in the elements it left behind, in the altered spin of the neutron star, and in the smooth transition it provided between the violence of birth and the permanence of survival. The universe's most invisible energy source has shaped one of its most tangible relics. From the core that once collapsed beyond imagination, the faint breath of neutrinos has carried the last exhalation of heat into space. The wind fades, the light dims, and what remains is a star that will outlast the echoes of its own explosion, a neutron star fully formed, cooling quietly in the afterglow of its creation. When the proto-neutron star completes its transition into a stable form, it carries within it the rotational memory of its parent star. The collapse that reduced the core from a radius of millions of kilometers to only a few tens has concentrated angular momentum to an extraordinary degree. Conservation of spin compresses the slow rotation of the progenitor into astonishing speed, so that the newborn neutron star may turn on its axis several hundred times per second. This rapid rotation reshapes everything that follows its magnetic field, its emission, and its long-term evolution. What was once the faint magnetism of an ordinary star is now intensified by many orders of magnitude, transforming the remnant into one of the most magnetic objects in the universe. The relationship between rotation and magnetic field becomes inseparable, and together they define the next phase of its life. Magnetic fields originate from the electrically conducting fluid that fills the neutron star's outer layers. During the collapse, differential rotation between the inner and outer regions of the proto-neutron star twists these magnetic lines of force into spirals, amplifying them through a process known as the dynamo effect. Small seed fields from the progenitor star, perhaps only a few thousand times stronger than Earth's, grow to become trillions or even quadrillions of times as intense. At these magnitudes, magnetism exerts pressure comparable to gravity itself. The fields thread the dense matter of the crust loop through the interior and extend outward into the surrounding vacuum. Some are anchored deep in the solidifying layers, while others rise through the surface, forming magnetic poles. The configuration may be roughly dipolar, like a bar magnet, or complex and tangled, depending on how turbulence froze at the end of the convective phase. The rapid rotation of the neutron star causes these magnetic fields to move through space, inducing electric fields that accelerate charged particles along the magnetic lines. The interaction between rotation and magnetism transforms the neutron star into a gigantic unipolar generator. In the regions near its magnetic poles, charged particles are ejected in beams that move outward at relativistic speeds. These beams will later become visible as pulses of radiation when the star's rotation sweeps them across an observer's line of sight. The phenomenon gives rise to pulsars, the most direct observational evidence of neutron stars. For now, in the minutes following formation, the emission remains trapped behind the opaque debris of the supernova, but the processes establishing it are already in motion. Inside the star, the magnetic fields interact with the dense fluid in complex ways. The core, composed mostly of neutrons, conducts little electricity, but a small fraction of protons and electrons forms a superconducting mixture capable of sustaining currents indefinitely. In these conditions, magnetic flux is confined into narrow filaments that thread through the superconducting material like invisible strands. As the star spins, these filaments couple to the vortices of the superfluid neutron component, locking rotation and magnetism together. The behavior of the entire star becomes governed by this internal linkage. Changes in rotation can rearrange magnetic structures, while the shifting of magnetic stresses can alter spin. Over time, this interaction will produce the glitches and irregularities later observed in pulsars' tiny adjustments that reveal the hidden quantum fluid within. The energy contained in rotation is immense. A neutron star spinning 100 times per second holds more kinetic energy than the sun emits in 1,000,000 years. Yet this energy is not static. It leaks away through electromagnetic radiation and particle winds. The rotating magnetic field acts as a braking mechanism, generating torque that gradually slows the star's spin. This spin down occurs steadily, its rate determined by the strength of the magnetic field and the rotation speed. As the neutron star ages, its period lengthens, and the energy loss powers the surrounding nebula with streams of high-energy particles. The famous Crab Nebula, the remnant of a supernova observed 1,000 years ago, shines today because of such a central engine, a rapidly rotating neutron star feeding its surroundings with rotational energy converted to light. In the immediate aftermath of formation, the magnetic field may evolve quickly. The crust, still plastic in its early state, allows the field lines to move and rearrange. Magnetic stresses twist and reconnect, releasing bursts of energy that heat the outer layers. In extremely magnetized stars known as magnetars, these adjustments produce X-ray and gamma-ray flares far more energetic than ordinary pulsars. The origin of magnetars likely lies in proto-neutron stars, where rotation was fast enough and convection strong enough to amplify the magnetic field beyond the threshold of stability. When such a field freezes into the crust, it can store vast amounts of tension later released as sudden bursts of radiation. Most neutron stars, however, form with moderate fields that evolve quietly, their surfaces cooling and solidifying without major eruptions. The relationship between magnetic field and rotation also governs how the neutron star communicates with its environment. The rapidly rotating field creates an electromagnetic bubble around the star known as the magnetosphere. Within this region, charged particles are trapped by magnetic forces and co-rotate with the star. Beyond a critical radius, the particles can no longer keep pace with the rotation, and the field lines open into space, allowing plasma to escape. The boundary between these regions defines the shape of the pulsar's emission beams. In the earliest moments, the magnetosphere may still interact with the supernova ejector, driving shock waves that contribute to the structure of the expanding remnant. As the supernova debris thins over months and years, the radiation from the neutron star becomes visible. Pulses of radio-optical and X-ray light appear, each corresponding to a rotation. The regularity of these pulses, governed by the precise spin of the neutron star, will allow observers to measure its slowing rate and infer its magnetic strength. Every detected pulse represents the conversion of rotational energy into radiation through the star's magnetic field. What was once hidden now becomes a cosmic lighthouse, its rhythm revealing the laws that shaped it. Within the neutron star, the interaction between magnetic field and rotation continues to evolve for millennia. The crust gradually cools and hardens, locking the field in place. Over time, magnetic diffusion and slow crustal movement cause the field to decay, reducing the torque and allowing the spin down to slow. The star's emission fades, but the internal field remains strong enough to guide charged particles and maintain residual activity. In magnetars, stresses within the crust can still rearrange field lines after thousands of years, producing sporadic bursts that echo through the surrounding nebula. Each flare is a reminder of the energy stored at birth, the remnant of motions frozen in the moment when matter solidified from fluid to crystal. The rotational and magnetic character of each neutron star defines its future identity. Some will remain fast-spinning pulsars for millions of years, gradually slowing as they radiate away their energy. Others will evolve into magnetars, their decaying fields powering bursts of high-energy light. A few will eventually accrete new material from companion stars reawakening as millisecond pulsars. All trace their properties back to these first minutes of existence when differential rotation convection and neutrino-driven currents sculpted the magnetic skeleton that endures through time. The proto-neutron star's violent past has become encoded in fields and spin invisible yet permanent, ensuring that even as the light of the supernova fades, the core will continue to broadcast its presence across the universe through pulses, radiation, and the silent shaping of space around it. After the outward surge of the supernova fades into expansion, not all material achieves escape velocity. In the inner regions of the ejector, a fraction of the gas slows, reverses direction, and begins to fall back toward the core. This process, known as fallback accretion, represents gravity's last attempt to reclaim what the explosion tried to cast away. The density gradients in the ejected layers, the irregularities in shock propagation, and the gravitational well of the neutron star all conspire to draw some matter inward. Within minutes to hours after the explosion, streams of heavy nuclei, protons and neutrons begin to rain back upon the newborn star. What had been an expanding cloud of ash becomes in part a returning storm. The mass involved in fallback is small compared with the total ejected mass, but its influence is profound. Even a fraction of a percent of the Sun's mass returning to the neutron star can release more energy than 1,000 normal stars radiate in a year. As this material collides with the dense surface, it converts gravitational potential energy into heat, creating brief but intense flashes of X-rays and neutrinos. The infalling matter does not strike uniformly. It forms streams and clumps guided by turbulence and magnetic fields left behind in the explosion. The impacts shake the outer crust, reheat the atmosphere, and may even alter the magnetic configuration frozen into the surface. Each event contributes to the early thermal evolution of the star and helps define its final mass and rotation. The behavior of fallback material depends strongly on the energy of the original explosion. In powerful supernovae, the outward-moving shock leaves little opportunity for return. The ejected matter expands too quickly, and only a thin residue of gas falls back. In weaker explosions, the shock may slow as it moves through the outer layers, allowing large portions of the envelope to remain gravitationally bound. This material begins its return within minutes, forming an accretion flow that feeds the neutron star for hours or even days. In some cases, the returning matter may be sufficient to push the mass of the neutron star beyond its stability limit, causing it to collapse further into a black hole. The delicate boundary between survival and final collapse depends on the combined mass rotation rate and energy of the ejected layers. As the fallback proceeds, the returning material forms a transient disk around the neutron star. The gas-carrying angular momentum from the asymmetric explosion cannot fall directly onto the surface. Instead, it orbits and gradually spirals inward, heating through viscous friction. This accretion disk radiates energy across a wide range of wavelengths from X-rays to soft gamma rays as matter gradually loses angular momentum and settles onto the star. The accretion phase may be brief, lasting only a few hours, but in that time it can add measurable mass and redistribute angular momentum, slowing or in some cases spinning up the star. The infalling matter also delivers new magnetic flux, distorting or amplifying the field embedded in the crust. The process of accretion introduces compositional diversity. The material falling back is rich in heavy nuclei synthesized in the supernova's innermost layers. When this material strikes the hot, dense surface, nuclear reactions resume breaking and reforming nuclei in bursts of fusion. The outermost layers of the neutron star thus become a patchwork of newly created isotopes, some stable, others radioactive. Over time, the radioactive species decay, releasing heat that contributes to the slow cooling of the crust. In this way, fullback accretion acts as a late-stage furnace, reshaping the chemical and thermal boundary of the star after its initial formation. For several hours after the explosion, the balance between inflow and outflow continues to shift. As neutrino emission weakens and the shock's expansion slows, gravity gains ground. Some regions near the equator may experience persistent inflow, while polar directions remain clear due to magnetic field lines channeling material outward. This asymmetry further imprints structure onto the forming magnetosphere. The inflowing gas guided along magnetic channels can produce short-lived hotspots, where it impacts the surface. These regions radiate thermal X-rays that in later stages may be visible through the thinning debris of the supernova remnant. The pattern of these hotspots can influence the star's future emission geometry, establishing the alignment between its spin and magnetic axes. If the explosion was exceptionally asymmetric, fallback may occur unevenly, delivering momentum that kicks the neutron star in a particular direction. Observations show that many neutron stars move through space at hundreds of kilometers per second, a relic of this process. The uneven pressure from the collapsing gas and the recoil from asymmetric accretion flows provide the impulse that propels the compact star away from the explosion's center. Over thousands of years, this motion carries it through its expanding nebula, leaving a trail of disturbed gas that marks its passage. The combination of recoil and rotation gives each neutron star a unique trajectory and spin a silent record of the complex forces that shaped its origin. As the rate of fallback declines, the accretion disk thins and fades. The star's intense gravity continues to attract isolated fragments, but most of the nearby gas has already been ejected beyond return. The last infalling material adds only a thin coating of fresh nuclei to the crust. The energy released by these impacts dissipates through the neutron star's surface layers, contributing to the residual heat that will radiate for thousands of years. When accretion ceases entirely, the neutron star enters a new phase of thermal relaxation, cooling solely through internal conduction and neutrino emission. In the broader supernova environment, the cessation of fallback marks the completion of the transition from explosive to stable expansion. The surrounding ejecta continue to move outward, unimpeded, forming the characteristic shell that will expand for millennia. Within that shell, the neutron star stands isolated. The once violent connection between core and envelope has ended. From this point forward, the compact star evolves largely in isolation, influenced only by its own magnetic fields and the distant gas of the remnant. The effects of fallback endure in subtle ways. The additional mass it contributes alters the star's internal density profile, affecting its long-term cooling rate and magnetic evolution. The angular momentum transferred through accretion modifies its rotation period, setting the initial conditions for its future as a pulsar or magnetar. The chemical deposits from returning material determine the composition of the outer crust, influencing how it crystallizes and conducts heat. Even the direction of its motion through space may trace back to these moments when the dying star still exerted control over its remnants. In the cosmic sense, fallback accretion represents the closing gesture of a supernova. The explosion that once scattered matter across space briefly reclaims part of it, ensuring that no energy is wasted. The returned material compresses heats and then becomes part of the permanent body of the neutron star. Gravity, momentarily defeated by the shock, has the final word in shaping the survivor. The neutron star emerges not as a pristine sphere, but as a complex layered structure sculpted by returning matter. marked with traces of its violent beginning. Around it, the remnant expands in silence, while at its center the dense core continues to hold the memory of both collapse and return, a balance between what was expelled and what was reclaimed by the force that created it. Once the last waves of fallback fade and the proto-neutron star settles into equilibrium, a slower and quieter process begins. The dense object that survived the explosion is still extraordinarily hot, radiating energy in the form of neutrinos from every layer of its interior. These emissions, though invisible, represent the final major channel through which the new star loses its residual heat. For the first minutes of its existence, the luminosity in neutrinos surpasses that of any ordinary star in the universe. Gradually, over tens of seconds, this torrent subsides, marking the end of the protophase and the start of a new regime governed by cooling and solidification. The violent phases of collapse, shock, and accretion have passed. What remains is the slow transformation of a fluid sphere into a crystalline solid under unimaginable pressure. Inside the neutron star, matter exists at densities beyond those found anywhere else. The deeper layers are dominated by neutrons, but the outer regions still contain a small fraction of protons and electrons. As the temperature drops below a few billion degrees Celsius, the motion of particles slows, and the star's surface begins to transition from a liquid-like plasma to a structured arrangement of nuclei. The first layer to solidify is the outermost, where density is lowest. Atomic nuclei here assemble into an ordered lattice, surrounded by a sea of degenerate electrons. This marks the birth of the crust, the solid skin that will encase the star for the rest of its life. Beneath it, matter remains in a dense fluid state, but the cooling continues inward, layer by layer, freezing the structure progressively. The crust grows thicker as time advances, extending downward until the pressure becomes too great for ordinary nuclei to survive. In this region, exotic forms of matter appear, nuclei stretched and compressed into rods sheets and complex patterns by the competing forces of nuclear attraction and Coulomb repulsion. Physicists refer to this regime as nuclear pasta, for the structures resemble lasagna, spaghetti, and other shapes at the microscopic scale. These formations represent one of nature's most intricate balances between order and compression. They exist only briefly until even higher densities transform the material into a uniform mixture of nucleons. While the crust hardens, the core continues to evolve through different physical processes. Neutrons within the central regions begin to pair up, forming a superfluid, a quantum state that flows without friction. At the same time, the small fraction of protons becomes superconducting, allowing electrical currents to move without resistance. These two properties, superfluidity and superconductivity, give the neutron star its remarkable internal dynamics. The superfluid can rotate only through the presence of quantized vortices, while the superconducting protons lock magnetic fields into narrow flux tubes. The interaction between these two networks of filaments and tubes controls the star's future behavior, influencing how it spins down, how it glitches, and how it radiates. As cooling progresses, the rate of neutrino emission changes character. Early on, neutrinos were produced by direct interactions between nucleons, but as the interior cools, these processes become inefficient. New mechanisms take over, such as pair breaking and recombination, where the formation and destruction of superfluid pairs release bursts of neutrinos. Each stage leaves a signature on the star's cooling curve, a record that astronomers can later infer from observations of surface temperature. Within a few hours, the neutron star's interior temperature drops to less than 1 billion degrees Celsius. The surface, now covered by a solid crust only a kilometer thick, falls even faster due to radiative cooling. The transition from fluid to solid does not occur uniformly. Thermal gradients across the crust create stresses that can fracture the forming lattice. These cracks release energy in sudden bursts, producing microflares of X-rays and gamma rays. In later stages, as the star spins and its magnetic fields evolve, similar fractures will generate the starquakes observed in magnetars and other neutron stars. For now, the crust is still settling, releasing the tension accumulated during solidification. The result is a gradual hardening that locks the magnetic field into place and defines the mechanical strength of the outer layers. Above the solid crust lies a thin atmosphere only centimeters thick. It consists mostly of light elements, hydrogen, helium, or carbon, depending on the composition of the fallback material. This atmosphere regulates the star's visible radiation by scattering and reprocessing the thermal emission from below. Though extremely thin, it determines the appearance of the neutron star when viewed in X-rays or visible light. As the crust cools further, the surface temperature stabilizes at a few million degrees Celsius, and the star begins to shine faintly in soft X-rays. Its light, though dim by stellar standards, reveals the cooling that will continue for millions of years. Beneath the crust, the layers of superfluid and superconducting matter maintain near-perfect equilibrium. The transfer of heat from the core to the surface now depends on conduction through this complex medium. The rate of cooling can vary depending on the presence of impurities, magnetic fields, and trapped particles. In some stars, rapid cooling occurs when exotic particles such as hyperons or deconfined quarks appear in the core, providing additional channels for neutrino emission. In others, cooling proceeds more slowly, leaving the star warm for longer periods. Each neutron star thus carries its own thermal fingerprint determined by the precise balance of physics that governs its internal structure. The solidification of the crust marks a turning point in the life of the neutron star. The chaotic motions of its birth give way to a stable, enduring form. The object is now a perfect balance of extreme forces, gravity, quantum pressure, magnetism, and nuclear physics, each frozen into equilibrium. The magnetic field lines that once moved freely within the fluid interior become anchored to the rigid crust, ensuring that the geometry of the field will remain stable for millions of years. Rotational energy trapped within the superfluid core is now released only gradually through electromagnetic braking. The star's evolution slows dramatically, entering an age of quiet persistence. For the universe beyond the cooling and crust formation of a neutron star occur in total silence. The surrounding supernova remnant glows in visible and radio light, but at the center the compact core radiates mainly in neutrinos and soft X-rays, invisible to most telescopes. Only the most sensitive instruments can detect its faint pulse of heat. Yet within this stillness the transformation is profound. The matter that once flowed like liquid now stands rigid under gravity's weight. The crust, though thinner than a mountain range on Earth, can support stresses that would shatter any known material. Beneath it, the core remains a quantum ocean, cold, frictionless, and dense beyond measure. By the end of its first day, the neutron star's crust is fully formed. The neutrino emission has fallen to a small fraction of its original brightness, and the temperature gradient between core and surface begins to flatten. The star will continue to cool slowly for the rest of its existence, releasing its heat through neutrinos for the first million years and through photons thereafter. Its structure is now stable, its composition fixed, and its destiny sealed. From this point forward, time stretches into vast stillness. The neutron star that once burned with the energy of a sun now glows with the quiet persistence of cooling matter, an object that will outlast the remnants of the explosion that created it. Deep within the neutron star, far beneath the crust and the layers of exotic nuclear matter, lies a region that defies ordinary understanding of states of matter. Here, temperature and pressure reach values so extreme that atomic and even nuclear structures cannot survive in their familiar form. The matter is composed almost entirely of neutrons, with a small fraction of protons and electrons interspersed, yet these particles do not behave like a conventional fluid. Instead, under the immense density many times that of an atomic nucleus, they enter quantum mechanical states that transform the core into a superfluid and a superconductor. In this domain, the laws of macroscopic physics give way to quantum behavior on astronomical scales. Every cubic centimeter of this interior contains more mass than a mountain, and yet the entire region behaves as a single coherent quantum system. The transition to these states begins when the temperature drops below a few billion degrees Celsius, only minutes after the neutron star's formation. The degenerate neutrons, forced into the lowest available energy states by Pauli exclusion, begin to pair through weak nuclear attraction. Each pair acts like a single particle with integer spin, allowing the ensemble to condense into a collective state that flows without resistance. This phenomenon, analogous to superfluid helium on Earth, but under vastly greater pressure, creates a liquid that can move indefinitely without losing energy. The paired protons, fewer in number but still mobile, undergo a similar transition. They form a superconducting phase that carries electric currents without resistance, locking the star's magnetic fields into narrow channels known as flux tubes. Together, these properties define the inner architecture of the neutron star, a superfluid core threaded by a rigid lattice of magnetic vortices. The dynamics of this core are complex. The superfluid neutrons can only rotate by forming quantized vortices, microscopic filaments around which all circulation is concentrated. The number of vortices corresponds directly to the rotation rate of the star, and their distribution determines how angular momentum is stored and released. These vortices interact with the superconducting flux tubes of the proton phase, pinning and unpinning in patterns that influence the star's spin. When large numbers of vortices suddenly move, the rotation rate can change in measurable jumps, events observed as glitches in pulsars. Each glitch reflects a rearrangement of the superfluid's internal structure, a brief communication between the frictionless core and the rigid crust above. The existence of superfluidity and superconductivity within neutron stars has far-reaching consequences for their evolution. The superfluid acts as a nearly perfect reservoir of angular momentum, preserving the star's rotation, even as electromagnetic braking slows its outer layers. The differential motion between crust and core builds tension that can only be released when vortices unpin and migrate outward, transferring angular momentum in bursts. This mechanism explains the sudden small increases in rotational speed seen in young pulsars such as the Vela pulsar. It also governs the gradual coupling between the star's interior and exterior, ensuring that the neutron star behaves as a unified object despite its layered complexity. The superconducting protons, meanwhile, play a key role in the magnetic behavior of the star. In a normal conductor, magnetic fields can diffuse over time, but in a superconductor, they become locked into place. The magnetic flux cannot move freely. It is confined within thin tubes that are anchored to the material structure of the core. As the star cools and its crust solidifies, these flux tubes become entangled with the lattice of nuclei and with the vortices of the superfluid. Over thousands of years, the slow motion and interaction of these structures lead to the gradual decay of the magnetic field as energy is released through friction and reconnection. In strongly magnetized stars, these processes generate the bursts and flares observed from magnetars, where magnetic stresses stored deep in the crust are suddenly discharged. At even greater depths, conditions may exceed those under which ordinary nuclear matter can exist. Theoretical models predict that the core could contain new forms of matter, hyperons, which are baryons containing strange quarks, or even deconfined quark matter, in which individual quarks move freely within a sea of gluons. These exotic states would alter the equation of state, changing how pressure relates to density, and therefore how the star's structure supports itself against gravity. Although such phases remain speculative, they are consistent with certain observational clues, particularly the rapid cooling seen in some young neutron stars, which might require additional neutrino emission channels provided by exotic particles. If these states do exist, they remain permanently hidden beneath tens of kilometers of solid matter, locked away within the star's center. Heat transport within this deep core follows paths unlike those in any normal material. Because the superfluid neutrons have no viscosity, they can carry heat efficiently through collective motion, while the superconducting protons conduct electricity without resistance. The result is an environment where temperature gradients are smoothed rapidly, leading to near isothermal conditions throughout the interior after only a few decades. The surface separated by the insulating crust remains much cooler, so energy continues to leak outward slowly through neutrino emission and photon radiation. Over hundreds of thousands of years, the entire star cools from billions to millions of degrees, but the superfluid core remains active, supporting quantized vortices that persist as long as rotation continues. The superfluid's presence also affects the star's response to external forces. When the crust deforms due to magnetic or rotational stresses, the core flows to compensate, maintaining hydrostatic balance. However, because the vortices are pinned to the crust, any sudden shift can cause partial decoupling between the layers, resulting in oscillations that may produce detectable gravitational waves. These minute ripples in space-time, though faint, could reveal the internal mechanics of neutron stars if measured by future observatories. The combination of superfluid flow superconducting currents and immense gravity makes each neutron star a natural laboratory for physics that cannot be recreated anywhere else. Over long timescales, the superfluid and superconducting properties evolve slowly. As the star continues to cool, the density of vortices decreases with spin-down, and the spacing between flux tubes increases. Magnetic energy decays through ohmic dissipation in the crust and through motion of flux tubes in the core. The star's rotation slows steadily, but the inner core retains its quantum coherence. Even after millions of years, when surface temperatures fall below the threshold for visible radiation, the superfluid still exists, flowing silently beneath the crust. It ensures that the neutron star remains dynamically stable, transferring momentum and heat in ways invisible to external observation. Eventually, as the magnetic field weakens and rotation slows to near stillness, the interactions between vortices and flux tubes diminish. The once dynamic superfluid core becomes quiescent, a perfectly ordered quantum state that no longer exchanges energy with the exterior. The star's interior remains frozen in its arrangement, preserved for geological ages. In this condition, the neutron star approaches the closest thing nature allows to absolute stasis matter, locked at nuclear density, motionless, yet stable, sustained only by the laws of quantum mechanics. It no longer shines, it barely rotates, but deep inside it still contains the silent echo of its creation, the memory of collapse, the legacy of pairing, and the unbroken lattice of magnetic and rotational threads that have endured since the first seconds after birth. When the neutron star has cooled enough for its crust to solidify and its surroundings to thin, it begins to reveal itself to the wider universe. The supernova remnant around it expands and fades and through the dispersing cloud the compact remnant starts to emerge as a distinct source of radiation. In its youth, the neutron star is still extraordinarily energetic. Its rotation is rapid, its magnetic field is strong, and its internal heat remains intense. These conditions combine to create a diverse population of observable objects, pulsars, magnetaires, and central compact objects, each reflecting a different aspect of the same physical foundation. The young neutron star is no longer defined by its collapse, but by how it now interacts with its surroundings through radiation, magnetism, and motion. The most common manifestation is the pulsar. When the magnetic axis of a rotating neutron star is misaligned with its rotation, axis beams of radiation emerge from the magnetic poles and sweep through space like the light from a cosmic lighthouse. Each rotation produces a pulse of radio or high-energy light for any observer aligned with the beam. The mechanism that powers this emission is the loss of rotational energy, as the neutron star spins its magnetic field, acts as a generator, accelerating charged particles along field lines and creating electromagnetic radiation. Over time, the rotation slows, converting spin energy into luminous power. In the earliest years, these pulsars spin hundreds of times per second, their pulses so regular that they rival atomic clocks. The Crab pulsar, born from a supernova recorded by astronomers in the year 1054, still rotates 30 times per second nearly a millennium later. Other young neutron stars exhibit even more extreme behavior. In a smaller subset, the magnetic field exceeds 10 to the power of 15 Gauss thousands of times stronger than that of an ordinary pulsar. These are magnetars where magnetic energy dominates every other form of output. The crust of a magnetar is under constant stress from the twisting and shifting of the internal field. When that stress exceeds the crust's strength, it fractures, releasing bursts of X-rays and gamma rays that can outshine an entire galaxy for seconds. Between these eruptions, magnetars emit a steady glow powered by the slow decay of their immense fields. Their lifespans as active sources are short only tens of thousands of years, but during that time they reveal the full intensity of magnetic physics at nuclear density. A third category, the central compact objects, occupies a quieter place in this spectrum. These neutron stars are found at the centers of supernova remnants, but show little or no radio or gamma ray activity. They emit steady thermal radiation from their hot surfaces, revealing temperatures of a few million degrees Celsius. Their magnetic fields are weaker or more complex than those of pulsars and magnetars, and their rotation rates are modest. To observers, they appear as isolated soft X-ray sources, reminders of the transition phase between the explosive birth and the later magnetically active life of a neutron star. Some may evolve into pulsars as their magnetic fields reconfigure or become visible through different wavelengths as their surfaces cool. The behavior of all these young neutron stars depends on three main parameters: mass rotation and magnetic field. A heavier star has a denser core and may cool faster through enhanced neutrino emission. A rapidly spinning star retains more rotational energy to power emission, while a stronger magnetic field amplifies the loss of rotational energy, but also drives more dramatic magnetic activity. The interplay among these factors determines the observable signature and longevity of each neutron star's active phase. As they radiate, spin down, and cool, their appearance shifts from bright and violent to faint and stable, tracing a continuous path of evolution over millions of years. Around many of these newborn stars, the expanding supernova remnant glows with synchrotron radiation light, produced by electrons spiraling around magnetic field lines at near light speed. The pulsar's wind composed of these charged particles collides with the slower-moving ejecta, forming a bubble of relativistic plasma called a pulsar wind nebula. The Crab Nebula is the archetype of this process, its filaments illuminated by particles injected by the central pulsar. The nebula expands, gradually shining for thousands of years as it converts rotational energy into light. The interaction between pulsar and nebula provides a window into the transfer of energy from the neutron star's interior to the cosmos. In some systems, the neutron star does not remain alone. If it was born in a binary system, it may eventually begin accreting material from a surviving companion star. The infalling matter forms a disk around the neutron star, heating to millions of degrees and radiating X-rays. Such systems, known as X-ray binaries, reveal the gravitational power of the compact star as it draws material from its partner. Accretion also alters the star's rotation, spinning it up to even higher frequencies. Over time, some neutron stars achieve rotation periods of only a few milliseconds, becoming millisecond pulsars. These objects, although old in cosmic terms, are reborn through interaction with their companions, demonstrating the continuous recycling of energy in the universe. The magnetic fields of young neutron stars also shape their surroundings beyond the immediate remnant. Their powerful magnetospheres sweep through the interstellar medium, accelerating particles and creating shock fronts that emit radio and X-ray radiation. These outflows inject energy and high-energy particles into space, contributing to the cosmic ray population that permeates galaxies. Even after the supernova remnant disperses, the pulsar wind continues to sculpt its environment, leaving bow-shaped shock waves as the neutron star moves through space at hundreds of kilometers per second. Each one becomes a moving engine of radiation, carrying the signature of its birth through interstellar space. Despite their ferocity, the young neutron stars cool rapidly. Within a few thousand years, the internal temperature drops to around 1 million degrees Celsius, and the thermal radiation fades. The magnetosphere remains active, but its power source shifts from heat to rotation. The star's visible light disappears, replaced by radio pulses, or in the case of magnetars, bursts of high-energy radiation. The transition from thermal to non-thermal emission marks the end of the star's infancy and the beginning of its long adulthood. What remains is a compact, stable object whose future will be measured not in seconds or years, but in millions of rotations. Each young neutron star is a record of the physical conditions that created it. Observations across the electromagnetic spectrum from radio to gamma rays reveal the structure, composition, and evolution of these objects. They provide natural laboratories for testing theories of matter, under extreme pressure for studying the behavior of magnetic fields beyond any achievable in laboratories, and for exploring how quantum processes shape macroscopic bodies. Every pulsar pulse, magnetar flare, or faint thermal glow from a central compact object is a signal from matter pushed to its ultimate limit. Over time, the brightness of these stars declines, but their endurance is remarkable. Long after their supernova remnants fade into the background of interstellar space, the neutron stars remain invisible, except to the most sensitive detectors. Some will continue to send out radio pulses for tens of millions of years, others will fade into silence, and a few may merge with companions to produce even more powerful explosions. But all share the same origin in the collapse of massive stars and the same foundation in the physics of nuclear matter. In the early centuries after their birth, they are young and active, broadcasting their presence across the cosmos. Later they will become quiet and cold, but even then they endure as fossils of the most violent transformation in the stellar life cycle, proof that from the death of a star, a new kind of star is born, As centuries pass after the supernova, the neutron star's energy drains steadily into space. The surface that once glowed at millions of degrees fades to a faint ember. Inside, the dense core retains its superfluid order, but without the heat of formation, it no longer drives convection or turbulence. The magnetic field, once violent and active, begins to decay as the crust resists further movement of trapped flux lines. Rotation slows under the constant breaking of magnetic torque. The pulses that once flashed across space stretch apart, weaken, and finally vanish from detectability. The neutron star enters a phase of quiet endurance, where change unfolds not over years or centuries but across geological and cosmic time. Its brightness dims, its emissions fade, but its structure remains perfectly stable. In the first 100,000 years, cooling continues mainly through neutrino emission from the inner core. These particles still carry energy away far more effectively than photons, but as the temperature drops below a few 100 million degrees, their production rate declines sharply. The balance of energy transport shifts from neutrinos to surface radiation. Now the heat must flow outward through the solid crust and escape as soft X-rays and ultraviolet light. This process is slow. The crust acts as an insulator, and the difference in temperature between core and surface gradually evens out. The surface cools to only a few 100,000 degrees Celsius, faint enough that only the most sensitive instruments can detect its glow. To the naked eye, even the youngest neutron stars have long vanished into the background of the galaxy. During this stage, the internal structure of the star remains unchanged. The superfluid neutrons continue to support the star's rotation, transferring angular momentum to the crust as the exterior slows. Occasionally pinned vortices in the superfluid break free, releasing small bursts of angular momentum that briefly accelerate the surface. These events, known as glitches, are reminders that beneath the rigid shell lies a fluid world still capable of motion. Each glitch is followed by a slow recovery, as the interior and crust realign, demonstrating that even after thousands of years, the neutron star is not entirely static. The combination of rigidity and fluidity allows it to maintain equilibrium while still responding to internal stresses. Magnetic decay continues throughout this period. The electrical currents that maintain the field slowly dissipate as they diffuse through the resistive crust. In ordinary pulsars, the field strength decreases over millions of years, weakening the electromagnetic torque that slows the rotation. The pulses grow dimmer and less frequent until they vanish entirely. In magnetars, the process is more dramatic. The immense stresses stored in the crust release episodic bursts of radiation until the field finally relaxes. After this phase, even magnetars become quiet, their magnetic energy spent. What remains is a cold, magnetically inert star spinning slowly in the dark. The cooling of the interior reaches equilibrium after about 1 million years. By then, the temperature has dropped below 100,000 degrees Celsius, and the emission shifts from X-rays to faint infrared radiation. At such low temperatures, the crust becomes extremely rigid, able to withstand enormous strain without deformation. The core remains superfluid, but the rate of vortex movement declines as rotation slows. The entire star settles into a state of near-perfect stability. Its density, pressure, and structure will remain constant for billions of years, preserved by the balance of gravity and neutron degeneracy pressure. Only external influences such as collision with interstellar matter or interaction with a companion star can alter its fate. In some cases, the neutron star continues its journey through the galaxy, at high velocity propelled by the recoil from its birth. It travels silently, ploughing through interstellar gas, its magnetic field, compressing the plasma ahead into a faint bow shock. The wake it leaves glows faintly in radio waves and X-rays marking its passage. Yet to distant observers it is invisible, an unlit remnant moving among the stars. Over time it may drift into regions of higher density, where interstellar matter accumulates on its surface. This slow accretion can generate faint bursts of X-rays, reigniting the star briefly before it cools again. The process may repeat over millions of years, each episode adding a thin layer of new material to the crust. For the vast majority of neutron stars, however, the long cooling ends in darkness. Their internal energy exhausted, they become essentially invisible except through gravitational influence. They persist as cold, heavy spheres, each with the mass of the Sun compressed into the size of a city. The matter inside remains locked in its quantum state, unaffected by time. These stellar corpses may drift for billions of years, orbiting the galaxy's center like silent relics of an earlier age. Some will eventually encounter other stars or be drawn into binary systems, reigniting through accretion and becoming X-ray pulsars once more. Others will continue alone until the end of cosmic time, their interiors cooling so completely that even neutrino emission ceases. The universe holds an enormous population of these remnants. Though only a fraction have been detected, models suggest that our galaxy contains hundreds of millions of neutron stars each, the result of a supernova that occurred over its long history. Most remain hidden, their radiation too faint to detect their signals, too weak to rise above the background of space. Yet they are among the most common outcomes of stellar evolution, reminders that even death in the cosmos leads to endurance. Every neutron star represents a balance achieved between destruction and permanence. As the epochs stretch on their rotation, may finally cease, leaving them completely inert. Without motion or heat, the distinction between core and crust becomes purely theoretical. The object becomes a single frozen sphere of nuclear matter. If the universe lasts long enough, proton decay or other quantum processes might eventually erode it, but on any observable timescale the neutron star will remain unchanged. It has reached the ultimate expression of stability, cold, dark, dense, and timeless. Even in silence, these stars influence the galaxies that contain them. Their gravity shapes the motions of nearby gas, their collisions produce gravitational waves, and their mergers create bursts of light and matter that seed the cosmos with gold and platinum. From the quietest neutron star to the most violent merger, they participate in the endless cycle of matter and energy that defines the universe. Each began as the remnant of a single star that lived, burned, and died, and each will persist as one of the most durable forms of matter ever created. The long cooling is not an ending, but a settling. What was once an inferno of collapse and radiation becomes a sphere of absolute calm. The neutron star no longer radiates enough heat to shine, no longer spins fast enough to pulse, no longer changes fast enough for time to seem relevant. It exists suspended between gravity and quantum pressure, waiting in the dark. In its stillness lies the final stage of a process that began with explosion and fire, the quiet persistence of matter beyond decay, a remnant of violence turned into permanence. The light that once marked its death has faded, but the object it left behind endures unchanging, indivisible, and eternal in its silence.